3.5 Optimization. Southwestern College, Professor Maria Olivas. Optimization. Objectives. Solve applied maximum and minimum problems. Optimization. The process of finding the maximum or minimum value of a function on a given interval. But what if you are given an optimization problem in context? In other words, you are not presented up front with the function that is to be optimized. You may find these guidelines helpful in solving such problems. 1. If the problem involves a geometric situation, draw a picture and assign your variables. 2. Write a function to represent what is to be optimized, that is, what is to be maximized or minimized. This is often referred to as the objective function. Consider any restrictions on values for your variables, that is, the interval of interest. 3. If the objective function is expressed in terms of more than one variable, you may need a constraint equation. This would be some equation that relates the variables involved. 4. Use your constraint equation to solve for one variable in terms of the other. Substitute this into the objective function to create a function in terms of a single variable. 5. Differentiate your new objective equation to find the possible locations for a maximum or minimum. If appropriate, consider the endpoints of a restricted interval. Example 1. A farmer wishes to create a rectangular corral for his horses. Situation 1. If he has 1,400 feet of fencing available, what dimensions will maximize the area? So in this problem, it says that the farmer wishes to create a rectangular corral. We're going to need to use a little bit of what we learned in geometry for our geometric formulas. Because it's asking for a rectangular corral, I'm going to need to use some of my formulas for a rectangle. It is providing us here with the 1,400 feet of fencing available, and that 1,400 feet of fencing represents our perimeter. So I'm going to draw a rectangle. I'm going to go ahead and label the sides. I'm going to label the two sides that are the longer sides, the sides that are on top and on the bottom of my rectangle. I'm going to label those with the variable x. And I'm going to label the two shorter sides, the side that's on the left and the side that's on the right, as variables with the variable y. And I'm also going to go ahead, I'm going to go back to the problem, and I'm going to go ahead and either box in or underline all the key things that were given to me in this problem. I'm going to start off by putting a box around the word rectangular. This was a key word because this let me know that I needed to focus on a rectangle. I'm also going to underline the part that said 1,400 feet of fencing available. That is providing me with the perimeter of the rectangle. And I'm also going to underline the part that says what dimensions will maximize the area? My objective here is to find a maximum. I need to find an equation that's going to help me find that maximum that will maximize the area. So let's go ahead and write down the formula for perimeter of a rectangle. I'm going to write down the word perimeter equals 2 times L plus 2 times W, which represents 2 times the length plus 2 times the width. And then I'm also going to write down the formula for area. I'm going to write down this formula right above where it says what dimensions will maximize the area. I wrote down the word area equals L times W, which represents length times width. So my lengths are going to be represented with the variable x. So I went ahead to my figure for my rectangle and I wrote L equals x, L equals x. And my y's are going to represent my width. So I represented those with a W. I went W is equal to y and W is equal to y. And now I'm going to go ahead and I'm going to write down my equations. One equation is going to represent my objective equation and the other equation is going to represent my constraint. Let's start off by writing down my objective equation or my objective function. So my objective here is going to be the area. I need to maximize area. So I'm going to go ahead and I'm going to write down here for area, A equals X times Y. We said that X represented length, Y represented width. So that would give me an equation that will provide me with the area. And for my constraint equation, I'm going to go ahead and use the information I know about the perimeter. I know that the perimeter has to be equal to 1,400 feet. So I'm going to go ahead and I'm going to write down here first, 2L plus 2W equals 1,400. And I'm going to replace L and W with X and Y. So it's going to be 2X plus 2Y equals 1,400. I'm going to go ahead and solve for Y. So I'm going to subtract 2X from both sides of my equation. And this is going to, the two X's are going to cancel out on the left-hand side. And we'll be left with 2Y equals negative 2X plus 1,400. Now I'm going to divide both sides of the equation by 2. So the 2's on the left-hand side are going to divide out. So I'll just be left with Y equals, and then we'll have negative 2X plus 1,400 all over 2. And if we simplify that equation, we get Y equals negative X plus 700. Because Y is equal to this, we can substitute this constraint equation into our objective equation. And that way we will have a variable in terms of X. So let's go ahead and do that. I'm going to draw a cloud around the expression negative X plus 700. That is what Y is equal to. And then I'm going to draw an arrow going up and over towards the right, pointing to the Y in our equation A equals XY. And now we're going to substitute. So A is going to be equal to X times the quantity. We're going to open up a set of parentheses and we're going to write in negative X plus 700 and then close the parentheses. I can then distribute the X to the negative X and the 700, and we will end up with the equation A equals negative X squared plus 700X. I am now going to find the derivative of A. So A prime is going to be equal to negative 2X plus 700. I'm going to rewrite the equation so it says negative 2x plus 700 equals 0, so we can find our critical values. We're going to subtract 700 from both sides of the equal sign, and then we will have our 700 and our minus 700 will zero out. And we'll have negative 2x equals negative 700. We will divide both sides of the equal sign by negative 2. The negative 2's on the left-hand side will divide out, and we will just be left with X is equal to 350. So this value of X is going to represent our critical value. I'm going to go ahead and draw a vertical line segment towards the right-hand side of the screen here in order to separate the work that I did here for my objective equation. And on the right-hand side of this vertical line segment, I'm going to draw a number line. I'm going to go ahead and plot that value of 350. I'm going to draw a little dashed line segment above it to separate the two intervals here on my number line. I have labeled my number line with the first derivative of A to show that this is going to represent our first derivative test. And then I chose test points on either side of the value 350. On the left-hand side of 350, I chose the test point of 0. On the right-hand side of 350, I chose the test point of 351. If I find A prime of 0, I get A prime of 0 equals negative 2 times 0 plus 700, which is equal to 700. That's a positive value, so I drew a little positive sign above the interval where the 0 is at, and I wrote INC underneath that positive sign to show that our original function of A is increasing in that interval. Then I found A prime of 351. A prime of 351 is equal to negative 2 times 351 plus 700. I ran out of space here, so I took all the work that I did here on the right-hand side of my vertical line segment that I had drawn earlier, and I lassoed it and I shrunk it. And I moved it slightly towards the left-hand side and slightly downwards. So now I'm going to go ahead and write here, a prime of 351 is going to be equal to -2. Because it's negative, I'm going to draw a negative sign above the interval where the 351 was located. And right underneath that negative sign, I'm going to write DEC, which stands for decreasing. That means our original function of a is decreasing in this interval. Since we went from increasing to decreasing, then this means that our value of 350 at x equal to 350, we are going to have a maximum. So in order to find that maximum value, we're going to go back to our equation that was solved for y, and we're going to substitute 350. So y is going to be equal to negative x plus 700, and we're going to substitute for x 350, so it's going to be y is equal to negative 350 plus 700. So y is equal to 350. Therefore, our dimensions of our rectangle are going to be 350 feet by 350 feet. These dimensions will maximize the area. Since these dimensions are equal to each other, the length is equal to the width, then this means that the shape that will maximize the area is going to be a square. I am also going to write down here below the dimensions that length is going to be equal to 350 feet and width equals 350 feet. And these are the measurements we need in order to maximize the area. Situation number 2. He is able to use an existing wall as one side of the corral, so only needs to fence in the other 3 sides. The fencing used for the side opposite the wall costs $2 per foot. The fencing used for the other 2 sides costs $3 per foot. If he wishes to enclose an area of 1,500 square feet, what dimensions should he use in order to minimize cost? Let's go ahead and draw a picture. I'm going to start off by drawing a rectangle, and this rectangle I'm going to draw one side that's going to represent the wall, the existing wall that's going to be used as one side of the corral. I'm going to use the top side of the rectangle to draw a horizontal line segment across one of those sides of the rectangle, and I'm going to write down the word wall so we know that that represents the wall. The remaining 3 sides, I'm going to label the opposite side of the wall as X, and the other 2 sides, I'm going to label those 2 sides as Y's. So each one of those sides is going to be equal to Y. I'm also going to write down on the side with the X, I'm going to write down $2 per foot because I know that side is going to cost $2 per foot. And the side next to the Y, I'm going to write $3 per foot. And I'm going to draw an arrow pointing towards both of the Y's so I know that both of those sides that have the Y's are going to cost $3 per foot. Now that we have drawn our picture, we are ready to come up with our equations. Let's go back to our problem and let's underline some key information that we need in order to write our equation. In the last sentence, it said, if he wishes to enclose an area of 1,500 square feet, what dimensions should he use in order to minimize cost? Let's underline to enclose an area of 1,500 square feet. And let's also underline what dimensions should he use in order to minimize cost? Our objective here is to minimize cost. So we need to come up with an objective equation that is going to represent cost. Let me go ahead and write down the word objective. I'm going to underline it and write a colon right after it. Underneath it, I'm going to write the equation that represents cost. It's going to be C equals 2 times X plus 3 times 2Y. And if I simplify this, it'll give me C equals 2X plus 6Y. So I'm basically multiplying the amount that is per foot for each side of the wall times the length or the measurement of that side of the corral that we're working with here. For our constraint, We need to enclose an area of 1,500 square feet. So area has to be equal to 1,500 square feet. And I know that the formula for area is going to be area is equal to length times width. A is equal to L times W. So instead of A, I'm going to replace the A with the 1,500. So we're going to write X times Y equals A. So X times Y equals 1,500. Now I'm going to solve this equation for Y and then substitute this into the other equation. I am going to divide both of these sides of this equation by X. The X's will divide out on the left-hand side, and we will be left with Y equals 1,500 divided by X. I'm going to draw a cloud around the part that says 1,500 divided by X and draw an arrow pointing up towards my cost or my objective equation. And I'm going to point it at the Y, where I'm going to substitute this. So C is going to be equal to 2X plus 6 times the quantity 1,500 divided by X. If I simplify this, I'm going to get C equals 2X plus 6 times 1,500 is going to be equal to 9,000, and that's going to be divided by X. C is equal to 2X plus 9,000 times X raised to the negative 1 power. And now I can take the derivative of this. So C prime is equal to 2 minus 9,000 times X raised to the negative 2 power. Now I'm going to go ahead and I'm going to take this equation and I am going to set it equal to 0 and I'm going to solve. So I'm going to write 2 minus 9,000 divided by X squared and set this equal to 0. Because I have a rational equation, I'm going to multiply both sides of this equation by the LCD. But first I'm going to lasso the equation and I'm going to move it slightly to the left. Now I'm going to draw parentheses around the left-hand side of the equation and multiply it by X squared. And I'm going to multiply the right-hand side of the equation by X squared as well. This is going to give me 2X squared minus 9,000 equals 0. Now I can go ahead and I can solve my equation. I'm going to add 9,000 to both sides of my equation. The minus 9,000 and the positive 9,000 are going to add up to 0, and I'll just be left with 2X squared equals 9,000. Now I'm going to divide both sides of my equation by 2. The 2's will divide out on the left-hand side, and I will be left with an X squared equals 9,000 divided by 2 is going to give me 4,500. Now I'm going to go ahead and I'm going to square root both sides of this equation. Let me go ahead and rewrite this equation with the square root. On the lower left-hand side of the screen, I'm going to write the square root of X squared equals plus or minus the square root of 4,500. So X is going to be approximately equal to 67.082 if we round to 3 decimal places. I'm only going to put the positive answer. I know that when we use the square root property in an equation, I do have a plus or minus that shows up. But because we're talking about measurement here in real life, real measurements, real lengths cannot have a negative measurement for length. So we're going to go ahead and just take into account the positive answer. I'm going to go ahead and draw a vertical line segment separating the work I've done so far from the work I'm going to do on the right hand side of the screen. I've drawn a number line. I've gone ahead and labeled my number line with a C prime, or the first derivative of C. I've gone ahead and I've also written down my critical value of 67.082. I'm going to go ahead and choose test points on either side of this value. On the left-hand side of this value, I'm going to go ahead and I'm going to choose the test point of 1. And on the right-hand side, I'm going to choose the test point of 68. Let's go ahead and substitute these values into the first derivative of C and see what we get. C prime of 1 is going to be equal to 2 minus 9,000 divided by 1 squared. 1 squared is just going to be 1. So C prime of 1 is equal to 2 minus 9,000. And then if I subtract these, I'm going to get C prime of 1 is equal to negative 8,998, because the value is negative, I'm going to draw a negative sign above the interval where we chose that test point of 1. And I'm going to write the letters DEC to represent that it is decreasing, that the original function of c is decreasing in this interval containing that test point of 1. Now we're going to find c prime of 68. C prime of 68. C prime of 68 is equal to 2 minus 9,000 divided by 68 squared. If we put this into the calculator, we're going to get C prime of 68 is approximately equal to 0.054. Because 54 thousandths is positive, I'm going to write a little plus sign above the interval where we chose our test point of 68, and I'm going to write the letters I and C that are going to represent the word increasing, because the original function of C is going to be increasing in this interval that contains 68. So now we got to find our value for y. So I'm going to go ahead and choose that equation that was solved for y, which was y equals 1500 divided by x. And I'm going to substitute in place of x what x was equal to. And I'm going to choose the exact value for x, which is the square root of 4500. So y is equal to 1500 divided by the square root of 4500, which is approximately equal to 22.361. Now we can go ahead and we can write down our measurements for these sides of this corral. So I'm going to go ahead and write down the side opposite wall is 67.082, and we're going to label the units as feet. The other sides are 22.361 feet each. And I'm going to go ahead and box that answer in. And that's going to be our final answer for this problem.